Our final speaker today is Robel Geda from Rutgers University, who has also been working with Bob Harmon this summer. He'll be discussing stellar surface imaging via light curve inversion.
So my name is Robel Geda, and I'm going to talk a little bit about light curve inversions. As Brandy explained, a star spot is basically a region, a cooler region on the surface of the star, and appears to be a lot darker, relatively darker, compared to the rest of the star, or the sun in that picture. And so it kind of appears black, pitch black, but really it's kind of bright if you isolated it and looked at it. And also, as Brandy explained, as the star, in this case Ellipticus, rotates, the star spot comes in and out of our field of view. This means that the intensity of light that we see from the star varies through time, so it kind of oscillates, becoming dimmer when it's in our field of view. And also, stars radiate similar to black bodies. So a black body is basically an object that absorbs all the radiation it receives and emits the radiation as a function of its temperature. And so you might notice that it's brighter in certain patches or in certain cross-sections of the electromagnetic spectrum. And so we use filters to kind of look at different varieties or different segments of the electromagnetic radiation that we receive from that star. And in this case, we've been using blue, visual, red, and infrared filters. And these filters are basically just pieces of glass with special coating on them that allow a specific range of wavelengths to permeate through them. And our instrumentation is Meade LX 600 telescope. And a CCD camera with the filters mounted inside of it. And the telescope is actually in this little dome that we lovingly call Little Perky. And this, and this is because this facility is Perkins Observatory that's operated by Ohio Wesleyan University. So after we have taken the images and performed the necessary image reductions, what we end up having is a light curve. So basically what the light curve is, and you look at Ellipticus, for example, in our case, and you determine its magnitude across different images that are taken at different intervals of time. And you can kind of plot them in this way, where you show rotational phase on the x-axis and the magnitude in the y-axis. And you can see the oscillation I was talking about, where the star spot is not present at the peak, and the star may seem dimmer when the star spot is present in our field of view. And so after we have this light curve, we can kind of take this and try and reconstruct the surface of the star. And this is done by an algorithm that was developed by Dr. Harmon, named light curve inversion, or LI in short. So basically what this algorithm is doing is it takes a sphere, or a disco ball, if you will, of radius 1, and divides it into small patches of equal angular width. And after you've done this, you also assume that each patch has is uniformly bright across its surface. After this, your LI algorithm, or your algorithm in general, has to account for certain things, such as the obvious being the sum of all the patches has to equal the total intensity that we see coming from the star. And other things, such as the location of the star spot kind of affects the light curve that we observe. And what I mean by this is, if the star spot is at the center of the stellar disk, we might see it be having a larger effect on the star due to a phenomenon called limb darkening, and that's just a fancy way of saying things at the edge of the stellar disk may appear dimmer to us. And across different filters, the severity of limb darkening can vary, and you can kind of gauge where the star spot is by using sort of this phenomenon, if you will. And so these are simulated star surfaces on the left. And on the right, basically what we did was we fed these simulated artificial stars to the LI algorithm, and we wanted to see what comes out. And as you can see, it does a pretty good job of kind of representing the surface, even though it might not be able to resolve close spots together. It does a very good job of kind of pinpointing roughly pinpointing where the star spots are located. And so something like this requires very kind of, not very, but advanced computational power. And we have a cluster called the Pleiades cluster at Ohio Wesleyan University. And even though we have powerful computers and are using very efficient software, it can take a very long time to generate a lot of algorithms. Well, that's an over-exaggeration. It can take quite a bit of time to do some of the calculations necessary to produce a stellar surface. And so what I have been working on this summer is kind of trying to speed up the computational process. And one of the ways that you can do this is through parallel programming. And this is basically, for example, serial programming, if you guys code, is if you had, for example, an array, and you wanted to go through each element of the array, which is just a set of items, you can go item by item and just process each item using all of the cores inside your computer. Or you can assign the task to multiple cores and have each core perform the process on each item of the array and kind of have the task performed simultaneously. So the more the cores, the merrier. So the more of the cores you have, the more things you can do simultaneously. And what has a lot of cores is graphic processor units, or GPUs. Initially, GPUs were developed for gaming. They were used for 3D game rendering. But soon after, the scientists saw this and said, this is interesting, there's a lot of cores in there, so we can use this. And so while a standard laptop these days has 4 cores, a GPU has thousands of cores. So you're able to do things simultaneously at a very large scale. For example, this is just a simple example. Let's say we have a set of numbers, 1 through 5, and we want to increment each element by 1, as in add 1 to each element. You could do this 1 by 1, as a serial CPU code would, or you could run a GPU and have each core add 1 to each element, and that's a lot faster, obviously. So in this case, I would say 2 birds with 1 stone, but in this case, so we've been doing well. In this case, in our case, we've been using Fortran as our base language, which has earned my respect this summer. And in combination with NVIDIA's GPUs, and they also have a library, a set of tools that you can use developed by the Portland group, and you can kind of use certain functions they already have, such as matrix multiplications and whatnot. And so, speaking of which, that's what we needed to happen. We had a matrix to vector multiplication that takes a lot of our time in computation. So we wanted to make that run a little bit faster. So what I've been doing is trying to integrate that into the code and kind of also reverse engineer for learning purposes the algorithm itself. And surprisingly enough, it actually really outperforms the CPU. And this is just a plot of a multiplication The x-axis shows the size of the matrix. So this is a 500 by 500, 1,000 by 1,000, and so on. And this is the time it took to perform the task. And this is also kind of accounting for, in the red curve, I'm sorry. The red curve shows the CPU's performance, and the purple curve shows the GPU performance. And this is also accounting for data transfer, because you have to transfer your data from your CPU to the device, and even then, it's actually really, really fast. And we have great hopes for this algorithm, and we hope to even make it even faster and implement it into our code. And special thanks to the NSF for this great opportunity with Ohio Wesleyan and Dr. Harmon. Basically, we're trying to look at the dot on a dot in the sky, so there's a lot of stuff that goes on to it, but if you guys have questions, I'll be more than happy to explain.
Okay, thank you, Robel. Questions? Yeah.
What GPU are you guys using?
We're using the Tesla K40.
K40. Yeah.
So I think last time I checked it was 2,400 cores, which is a lot, around there. That's still a lot.
Yeah.
What's the time complexity of matrix multiplication with regards to input size?
I'm sorry, actually.
What's the time complexity of matrix multiplication?
The complexity of
Time complexity, like based upon input size, how much does it change the time?
Oh, I'm sorry. So according to this plot, I haven't actually measured it, to be honest, but looking at this plot, it looks like an O of n squared. But this one also looks like an exponential function, but like I said, that's because of data transfer between the devices. I would expect it to run in a linear, I would have like a linear relationship if we didn't transfer. I didn't measure it though, to be precise.
So I know CUDA rather is traditionally like a C-based programming environment. So why Fortran, I guess?
So, so this is kind of like a lot of things playing together to kind of create this situation. The first and most important thing being the LI algorithm was initially made or written in Fortran. And so, you know, it would take a lot of effort to kind of translate it to C. And also, we were lucky enough to have the Portland group create an NVIDIA component where you could use it with Fortran. So instead of just copying everything to C and just doing CUDA and C, we just use Fortran. It's just very convenient.
Yeah, if they have that thing from Portland, why not?
Yeah.
Any other questions?
So the GPU has, what would you say, over 2,000 cores, but in the best case scenario here, we got maybe a factor of 3 speed up, it looks like. Am I reading that correctly? The very edge?
At the very edge, let's see.
With the largest matrix size?
So yes, the way I did it, also another thing is the cores actually have these things called threads in them, where you can assign, you can actually do more simultaneously than there are a number of cores, to be very specific. But in this case, like I said, it's the transferring the matrix from the device from your CPU to the device is what's like growing in an exponential manner, because you basically have to take the matrix and kind of feed it to each one of these devices. So if you took that out, I think that you would actually see the improvements. I thought it would be better.
And the good news is we can take it out for this application. So Robel, he was testing, and so he was doing it where he was. I think you were generating random matrices, right? And so you kept feeding the matrix to the GPU and taking it back again. But with the application, it's a matrix times a vector. The vector represents the surface that we're trying to find and optimize. The matrix that it's going to be multiplied by can actually sit on the GPU because it doesn't change. So we'll actually get a much bigger speed up than this in practice.
Okay, very good. Let's thank Robel again.